Welcome back everyone, and today we have another video and we're going to continue with more springs. I don't know if you guys are sick of springs yet, but we're almost done. This video and one more, and no more springs for a while. So the last three videos we've done a lot of things with springs: position, rotation, applying them to bones and chains of bones, and everything else. So now we're going to actually go really down and really apply spring physics to actual vertices themselves. So in this video we're just going to focus on vertices, and instead of just doing vertices like through through the CPU, we're actually going to push all our data into the GPU through buffers, and then we're going to use transform feedback to actually do all the computation and actually render. So this way all the work, all the movement is actually done completely on the GPU. There's no CPU whatsoever, so it's very optimized, very fast. It'll get things done really well. I've done videos about transform feedback, so if you don't know that topic, just go look at my playlist and you'll probably find a few. One specifically was related to transfer feedback, and anything related to particles also use transfer feedback. Today I'm gonna probably quickly go through the idea of what a transfer feedback, and I made a new version of transfer feedback which is simpler than the last version. The first version was the raw APIs. The second version was insanely complicated, and this one's kind of like close to the APIs but a very light wrapper for it. So this way it's bare bones, but it's still fairly easy to use to kind of just set up transform feedback. So we're gonna do we're gonna mess with some vertices, right? So here's an example called not an example of spring physics in general. This is a cartograph, and this inspired me to do something with springs and vertices. What this thing does, it actually just kind of just moves a bunch of dots, and I'm assuming it uses Portal and noise, and basically you control it, and you can just literally go traversing through some type of little world and see all the terrains. You can see plants. Apparently you can, this is kind of cool because you can leave little pins and like little messages, so it's kind of cool. It's kind of like this own little tiny little virtual world, and all it is just points. It's just vertices that get moved into position. So we're gonna rebuild something like this, something bare bones and simple like this, but we're going to add spring physics. So this way, or this one kind of just moves into position, which kind of probably does like a just a tween. We're going to spring our vertices into position. So like I said, we're going to build something like this. So if I go to the code, so if you're like coming from another game engine like Unity or something, transform feedback might not be something you're well aware of because it's something probably not given to you. That's kind of really a low-level thing. I don't think even 3GS has really much examples related to transfer feedback. I think there is when you're dealing with a lot of those big particle effects, but I don't really know how easy they make it set up for you. So like a quick primer, what is a transfer feedback? A transform feedback is basically kind of like a compute shader, but it's kind of like a poor man's compute shader. That's how I like to describe it. And the way I set it up is two steps. I make a shader code that just does computation, and I do another shader for rendering. And the rendering can be any normal shader that I have existing to begin with. Doesn't have to be tailor-made for the transfer feedback. The first version of the transfer feedback that I experimented with was actually one shader where you did transfer feedback inside your vertex shader, and then you did the rendering in your fragment shader. Since then, I've broken it out to the point where I just have just a vertex shader that does that computation, and I have the fragment shader turned off. So basically, like I said, I make it into a compute shader for a poor man. So the idea is you set up two sets of identical data. So let's say position, because we're going to deal with position, right? So I'm going to create a buffer A, all right? I'm trying to figure out the camera because it's a tiny look. So I got, you know, screw it. Using fingers is stupid. So I'm going to make a buffer A, right? And buffer A is going to have all my positions. How about I say this? No, I got my array, my position array. right? So I'm going to make buffer A, and I'm going to push the data right into it. So, you know, I can zip, right? So that goes into my buffer A. I'm also going to put that data. Oh my God. I wasn't even planning for this. I'm also going to put it into buffer B. Okay, so buffer B. So this array of information exists in two separate buffers. And when I do a transfer feedback, I read, let's say I'm going to read from A, but I'm going to write to B. And then I render the data from B. That's the first loop. In the next loop, like the next rendering loop, I read from B, I write to A, and I render from A. And it just becomes a circle. It's a feedback loop. You know, it's like if you deal with audio or anything, it's just a feedback loop. It just A feeds B, and then B feeds A, and then it becomes a cycle, a nonstop cycle. So you can always start off with identical buffers, right? Now the interesting thing is the way that I'm implementing it is that I create 4 VAOs. 4. 2 of them are to handle transform feedback, so it's A and B, and then another 2 VAOs which is to handle rendering, which is for A and B. And I can actually buffer A, which exists in VAO A, can also live inside VA. Oh my God, VAO A render. Oh, now I'm typing. So if I create this buffer, I can assign it to VAO A and VAO A render, like 2 different ones. So say this one VA compute. So that might make it easier. And there you go. So there you go. So like I said, we can do that, and we can VA computer. Compute. So we can have 2 VAOs that can actually share the exact same buffer, because all it is just references back to the buffer, and that's how we do. So we set up, like, let's say one, like I said, 2 buffers, and they're shared across. Well, yeah, they're shared across like 4 VAOs. So like I said, we do one set of A, and then we do one set of B, and that's it, and done deal. And that's really just the transfer feedback. And then when you have when I'm doing the transfer feedback, I actually disable the fragment shader. So this way it's purely just vertex shader. All right. So now you get the idea what that's all about. Let me shrink this down to video decent. I don't know. This is good enough. Make it bigger. There you go. All right. So we're going to do something simple. So so let's go to this, let's see, init file. Init, we're going to load in our shader. This is a compute shader that I put together. So we're going to look at that a little later. So we're just going to load it up, and this is going to be the rendering shader. So I have 2 shaders. I have I know I don't. What? Shader parse inline. That goes into JSON, and then JSON. So that is part of my compute shader, and I have to make a material out of it just because of how things work. So I go to setup. So now that with init initialization, we go setup. So setting up a transfer feedback, you kind of have to name the variables that get exported. That you're writing to, because in transfer feedback you have VAOs for reading, and then you create an actual object called transfer feedback that actually does the writing. So you apply. So when you create a buffer, you apply it to the VAO for reading, and you also share it to the transform feedback for writing. And when you do that, when you create a shader that does that, you have to give the variable name that's inside the shader that's going to handle the transfer feedback value. So we're going to pass in. We're going to have a target position we're going to have a follow position, and we're going to have a follow velocity. So I'm not going to go deal with actual springs. I have like 4 videos already about springs. So if you haven't figured out springs by now, it's tough. Go watch the previous videos. But we're going to basically do all the spring equations in GLSL. So those are going to be like our output variables that we save back into the buffer. Let's see, shader TS. Oh, this is our actual feedback. So this is our feedback. I guess the other shader in here is actually my renderer. This is my rendering shader, and this is going to be the one that exists in feedback is my feedback shader. So I'm actually building the shader here, passing in my vertex and fragment, and this is my fragment shader. Even though I'm not using the fragment shader to compile my vertex shader, I need the fragment shader. So you have no choice but to have a fragment shader. So it's like a super bare bones, doesn't really do anything because I'm going to disable fragment shaders when I actually do the execution. So you do still need it. So that's part of the thing. Like I said, it's a poor man's compute shader. So this is all kind of just helps sets up the compute shader. So that's all it is. So we're going to create our data. So we're going to, like I said, we need to create a grid. So I have an object that just creates all the vertices to create for a specific grid. So I give a size and I give it a dimension, and that's, it's going to have that many points. That same object, I say basically create indices of the grid. So this way I can actually have all the points, but then have all the dots connected as a grid. So this way, when I render, I can render points and lines at the same time. So I'm going to do double rendering. And this one does coordinates because for I can't remember why. It's been like probably almost a month since I touched this, but I should have reviewed it before making a video. But I know what that function does. It just gives me the coordinate. So every point I know the coordinate. That's right, because I need the coordinates to be able to do to use noise. So this way I can actually create the terrain. So what that does is like this vertex is coordinate 0, 0. The next one is 0, 1, 0, 2, 0, 3, so forth. So that's what I'm doing. So it's just the coordinate system. It's just the grid coordinate system for every vertex. So that's what the grid object exists on this page too. Everything's pretty much dumped on this page, so you don't have to go looking around for a lot of the code. And then I need one more shader. I think this is for the velocity. So I need the velocity. But I need to upload information to the velocity. And technically, I don't. I can actually set up an empty buffer. I just have to make sure the empty buffer has the exact byte size that I need to store it. But if the data becomes uninitialized, and that could be an issue. So to make sure I don't have any issues and no bugs, I just create a float 32 array of the size that I need for the velocity, and just zero it out. So this way I upload just an array of zeros into the velocity buffer. Let's see what else. So I'm going to create some buffers. So I have a new VAO object, and that allows me to just create buffers on the fly. So this is going to start being a little bit more like how 3GS does a little bit. So I kind of bounce back and forth between how I do things. But since this is kind of like a very custom setup, you kind of have to start building buffers at the low level. So instead of just using the other objects that I have, that's kind of like here's the vertex. I have objects that can just pass things in, and I just pass the data in, and it creates all the objects for me, and they call it a day. You don't really have to do the low level stuff that often. But for this specific case, you kind of do, because every transfer feedback is different. Unless you have like a collection of them that always share the same amount of data, there's no way to easily set it up. So you kind of have to build buffers at the near the API level. Like I said, there's still like a wrapper to make life easier. So that's what we're doing. So we're passing in our data, and this creates a new array buffer for us on the GPU, and it dumps the data and everything. So what we get back is the buffer itself. Same thing with this one. We just get back the buffer for the indices. This is for the generating the lines, and I have an object that I set up to handle just to contain the information to run the and it also has the run function too. So, and I set it up so this way I can pass in a setup function. So this way I can have, like I said, every transfer feedback is going to be different. So setting up the transfer feedback itself is going to be different, but when you execute it, it's always the same. So I could have that kind of like little middleman. So I just pass in a closure that actually does the setup for me, and then everything else kind of gets it can be reused for any other transform feedback. So it's a really nice small wrapper for transfer feedback I put together this time around. So like certain let's see, buffers are going to be shared because they're going to be read only, and some buffers are going to be read and write. So let's see. So we're going to have so what this does is that this is a setup. So that means this function is going to be run twice. It's going to be run for A and it's going to be run for B. That's why I pass in a closure. So this way I can set up how one is supposed to be set up, and it actually sets it up twice for two, so that we can actually go back and forth between the transfer feedback. All right, so let's see. So these buffers, the coordinates and the index, those are read only. So that's why they created outside of this function. Inside the function, they're going to be more dynamic. So like these are going to be shared between A and B. They're static. They're read only. So instead of creating these buffers, instead of duplicating the buffers for each one, I can create one buffer. I can create these two buffers, and they're shared within all the shaders. So there's like only one set of data. So that's what's going on here. So I have these built outside, and the ones that are pertaining to the A or B side of the transfer feedback, it's created inside the closure. So inside, for each side, we need the target position, the follow position, and we need the velocity because we're dealing with springs. So we're going to build the VAO for the transfer feedback. So we create a VAO for transfer feedback. We say we were going to add this buffer, and we do the index for the shader. That's what the final number is. And in case you're wondering, oops, I don't want that. If you go into Fungi Core VA2, like I said, this is kind of fairly new. Then here is where you'll find the buffer class. Like I said, it's just very short wrappers. Like this is the bare bones API. So it's like it's only one level of abstraction really, and like I said, it just keeps it very simple. So like building buffers, and then like I say, the brand new VAO objects the same way to handle those new buffers. Like I said, it's a lot of the simple low level things. So if you're really curious of what's going on with this stuff that's kind of new, just that's where it's in core, and it's called VAO2. Because there's a lot of stuff that uses VAO, so I can't just replace it. I have to slowly replace the old VAO with the new ones because it's a bunch of new functions and everything else. So I just add these buffers, and when I'm done, I do unbind everything, and then I set its element count because you have to set how many elements your No, I don't want to do that right now. And then we have to set up our transform feedback, and again, it's just it's the exact same buffers that we created, but we're setting it up in the transform feedback object. So that creates a transform feedback object, and this creates a VAO object. And then we have the VAO for drawing. So again, it's using this read-only one that's going to be shared, and it's going to use the follow position. So follow position is actually the position that we're going to actually be rendering. So that's where we're going to dump that in. So like I said, if you notice, everything kind of has like add buffer because everything is custom. But then when it comes down to here, it just add vertices. So when I say add vertices, it already knows all the configurations for vertices because all my shaders share the same bits of information. Like index 1 is for position, index 2 is for normals, and blah blah blah, yakety schmackety. So that's why I made VAO the new VAO. It makes it super simple because it's all configured to run the same thing. And And like I said, I'm doing 2 renders. So I'm going to be rendering, this one uses indices. So this one is when I'm going to render all the lines. And this one only has vertices. So this means I'm only going to render the points. So I'm double rendering, two renders. And they get 2 different element counts because this one is index length and this is vertices divided by 3. And that pretty much sets up the transfer feedback. And that is probably the end of the function. Then I just said node, and then that entity is now a global variable called terrain. And that's set up. I wasted so much time on that part. All right. Really, probably shouldn't waste too much time. Here's the grid. We'll just quickly look at it. Nothing special. It's just making grids of points. Like I said, this one makes all the line connections. So this way, the lines of a grid, so we can render out the lines. And again, this makes the X and Y coordinate system for it. All right, and this is the transfer feedback object. I said that kind of handles it. So I kind of have a pretty simple. You know, it just runs the build, passes in the shader, knows to use which entity, and then, like I said, this is kind of a hack. So it knows to take in, it knows it's going to do 2 draws. Ideally, it wouldn't know that if I'm going to render 1 or 2 or 3 things. So for this page, I kind of just hacked it together. And what's the constructor? And the constructor is we're going to have an array of data. So this when we do transfer feedback, we can actually just go back and forth between 0 and 1. Makes it super easy. So this way, if I say the current index is 0, that means I'm going to read from 0 and I'm going to write to 1. And then the next time, the current index will be 1, and I'm going to read from 1 and I'm going to write to 0. So I'm going to alternate back and forth. So that's how that works. So we're going to, like I said, we have the transfer feedback VAO. This is the transfer feedback object, and this is the draw VAO. Yep, but there's 2 of them, so whatever. And the build function, all it does is take that closure and run it twice, and it runs it twice using this information. So I pass in that element of the array, run the closure on it, then run it again on its own. So like I said, it's just quick setup for back and forth. And for executing, I have to shrink this down a little bit. And this is all the code needed to render a transform feedback. A lot of it, you can have to use you turn on the shader. You got to turn on. You got to bind your VAO. You got to bind your transfer feedback. Here, I disabled the fragment shader. This is when I actually run the shader. Then I turn the shader. Then I turn fragment shader back on because I'm going to do more. I want to render, so I need fragment shader turned on. So when you turn off the fragment shader, it's global. WebGL is a state machine. So when you set a state, it's global. So if you turn off something and you need it later, you got to remember to turn it back on. So it's good practice to make sure you keep track of what you're turning on and turning off, what you're binding it, what you need to unbind. So like I said, since I bound the transfer feedback, you got to unbind it, and everything gets unbound. So basically, you have all the setup, render, and then you undo the setup. And then after every transfer feedback, I kind of just swap the VAOs. Isn't that what I do? Yeah, I swap the VAO. So this way, VAO 0. So this way, and I swap in A or B's VAOs because the rendering system I have can't do that. It can't handle swapping back and forth. So that's what this component does. It just goes right into the draw component and just swaps it back and forth. So every time it just swaps the VAO's references for rendering, and then the actual object that does it, super bare bones. Like I said, this is like the raw API calls to set it up. So it's like bind, unbind, and how to bind a buffer to a transfer feedback. Very super simple. Very. So basically, it's kind of like our VO object, but much simpler. So next up is, this is the actual feedback shader. This is the compute shader that we're kind of working at. So at this point, like I said, these are all the buffers that we set up. Remember the numbers, here's the location values. And when you do a transfer feedback, remember I said there's 3 buffers and they have to name the variables, and here they are. They're the out variables. So I'm going to be reading from A, and this is going to be B that I'm going to be writing to, because I read from the VAO A, but then I write to transform B. And then on the second loop, I read from VOB, but then I write to transform A. So that's the thing. You got to swap back and forth a lot of things. So like I said, this is B, and this is A, essentially. This is the VEO, and this is the transform feedback object that's going to collect the information. But again, these kind of basically point to the same buffers. Like this points the shared data, but 2 different buffers. But there's the same information. You just go back and forth. We're going to pass in a uniform, and this is so this we can, like I said, that we're going to rebuild that map. So we're going to pass in the coordinate system for the noise, and this is the noise function I found online that works on GLSL. It's not Perlin noise, it's S noise, whatever. Good enough. I wanted something small and not massive, so it does a decent job creating noise, nice noise. And yeah, I just have some constant variables, and here is our semi-implicit equation. So this is the equation that we've been using for the last couple of videos, and I just basically translated it into GSSL, whatever. So we get our target position, and we have to. And one thing is you have to fill these in. Anything that's read and write has to be filled in. So you always have to say. So yeah, the target's updated. Yeah, target's updated because I'm always changing the Y, because I'm really actually just changing the Y position. So I pass in, I'm reading from A, I'm writing it to B, and updating the B's version with the Perlin noise height. I clamping it between 0 and the maximum height. After that, I start doing the spring equation. That's all it is. Just the regular spring equation we've been doing. So I'm doing the spring equation on the vertice target position. And that's, like I said, this is basically our entire compute shader. Very simple. You read a point, update it with Perlin noise, and since that's our target spot, we do the spring physics on that target spot. That's where we're trying to move to. And follow position is our current position, where target is where we're trying to get to. Just like all the other ones. And see, and this is the inline shader. This is just for rendering, and this is, like I said, this is a normal shader. The only reason why it's custom because I'm doing some fun stuff with it. I'm passing in an array of colors, and based on the height of the vertice, I'm going to do a different color. So let's see. So if let's see what we're doing here. So normalize the height. So this way, so based on the height, because I have a maximum height, so I'm going to normalize the current height, so between 0 and 1, and once the value is normalized, I'm going to, well, I have like 10 colors to choose from, or 7 colors to choose from. So it's normalized. Give me a normalized. So give me a value between 0 and 7. So that kind of creates the index, the point. Then I floor it because it's a fraction, it's a float, because I need access in an array's index. So that's why it needs to be in an int. So I need to floor it first and then int it. But at the same time, I want its fraction. So I have the integer value and I also want the fraction in between. So let's say if the height is like 1.5, my integer value is going to be 1. But I'm going to get the fract, which is 0.5. So to actually separate the values into two sets, I have the starting index, which I know the next index is +1, So that means I know I have color 1 and color 2. And that fraction is going to give me the fraction of that color. So I'm actually going to blend between color 1 and color 2. So if the color 1 is black and color 2 is white, and if I'm doing a halfway point, 0.5, actually I'm going to get gray. And that's it. So that's what I'm doing. I'm getting color 1, color 2, and TT is the fraction time. And then mix it together. I get a color in between. And that's it. And I pass that color to vary, which then goes into the fragment shader. And I use it to draw. And I'm drawing a circle. So instead of having black squares, like how I'm actually trying to make circle points instead. And that's it. So, like like I said, other than the transfer feedback, the big giveaway is really this piece. Like this is really the gist of the whole video, is applying spring physics to vertices. I'm sorry, I'm like my throat's dry. Doesn't help. I'm drinking iced coffee right now. So this is the original. Like this is what inspired me, because I wasn't sure what to do with vertices with springs, but then I saw this and then it gave me a great solution. So if I go to the test page, here we go. And like I said, this is all computing on the PC. And like I said, I can do left. And so every time I press a button, let me see. So I'm listening to the key down event, and depending on what button I do, I'm actually adding to the grid offset. So the grid offset is something I pass into the compute shader. It basically is saying, okay, we're moving through Perlin noise, and that's what I'm doing. I'm just moving through Perlin noise through an X. It's a 2D Perlin noise, so I have to give it an X and Y position, and then the grid values gives me the kind of like the offset. So let's say the grid starts at 0, 0, right? And the offset 0, 0. So I'm going to start Perlin noise at 0, 0. But if the offset is 1, 1, I'm going to add the offset to the starting point of the grid. So now the grid actually starts at 1, 1, and then that's it. And that's how I'm traversing through Perlin noise. And every time, let's say, like I said, every time I press down, I shift the offset, and then I tell it, I set the update offset, and then I think on a draw function, I check every render loop. I check to see if that's turned on. If it's turned on, I turn it back off. Then I say, well, transfer feedback, turn on the shader, pass in the new grid offset, and for every time we render, I'm actually executing the transfer feedback, because because I'm trying to, since everything is animating and then trying to move to a new position, I kind of have to render. At some point for optimization, you kind of want to stop when you know all the points are done. There's no easy way to know when the points are done. So I like arbitrarily, maybe you just automatically say, I'm going to run the animations for 5 seconds max, or like 2 seconds max. If the animation is running for 2 seconds since the offset has been changed, just stop executing. So this way you're not constantly executing the shader. Because all that compute shader is doing is just updating the position, and then the renderer just runs by itself through the render system. So yeah, there you go. And like I said, you can hold down the button and it just starts to wiggle, because now every frame you're changing the offset. And if I let go, everything kind of just springs into place. These spring. And I made the springs like that on purpose. Just so it's easy to visually tell that things are using springs. So you probably wouldn't want to make it so noticeable. Maybe you want to do like a very light spring, kind of just lightly springs into position, without this is wah 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 wah. And like I said, it's kind of cool because I set it up where the height changes the color. So the bottom is water. then you have that color which is kind of like your beach sand. Then you have green for grass, and then near the top is where snow is. So yeah, I could try to mimic this a little bit because I think they do have snow at some point. There's the water, and yeah, it goes up. I think there's this. This is kind of, I think, has some kind of biodome. So this is probably like the snowy area. Probably at some point I'll find a green area where there's grass. This looks like it might be more of a rocky by the looks of the color. I don't know. There's red. It's becoming a lot of red. Maybe I'm in the lava's area. I have no clue. I don't know. And there's like little objects in there, and I like the clouds that fly around. But there you go. Like I said, and there's like I'm rendering this thing twice. So I'm rendering all the points, and then I'm rendering all the lines. Let's see, how long is this video so far? 35 minutes. Wow, longer than I wanted to. I guess it took a minute. It's wasted too much time talking about transfer feedback, but it really is the kind of like how to get this working. But yeah, there you go. I hope you like it. This is kind of a fun project. If you've been following me on Twitter, you probably saw this like a month ago. I finally got time to sit and recording, and yeah, I've been busy. So yeah, so there you go. This is how you can apply springs to vertices, and you know, you can do a lot of things. Like you can, I don't know, whatever you want. It's like you can compute the movement. You can do particle physics. You know, you can have things just randomly, like maybe every 10 seconds you can have the points randomly going to new places. Maybe you can do a mesh. You know, you can have like a mesh, right? You can have like a mesh of a character, and then you can compute the points to rip apart and go flying in their own directions. Or they can implode weirdly, you know. That'd be actually kind of cool. Just have all the vertices kind of implode into a dot. I probably have to do that someday with a mesh. It just like implodes, and then like you like maybe you have like a read buffer, like a read only buffer that has the original position, and then at some point you say, well, now I want to put all these points and move them back into position, and you tell the shader, okay, stop imploding, now explode it back into position. So you can do some, you can be creative of how you want to move the points. And like I said, you can move these points, and then you can have spring physics where everything kind of springs into place. I am so sorry. So yeah, play around with it. Like you can take the sample off GitHub and play around with it and do whatever you want with it. If you want, you can build a cartographer competitor if you want to go that far with it. You know, it doesn't matter. Like I said, I built this for fun, and I thought that would be a great way to illustrate spring physics on vertices, like a bare bones simple one. In the next video, we're going to I'm just curious how. Ooh, no. Can I get a full screen? Is it 11? I can't get full screen. Oh well. I wanted to go full screen. I'm just curious how this might look. I think I did this before. Like I zoom in, and I'm like inside the area, and you see all the world kind of just shifts around you. So this might be cool if I actually rendered this out like as a full mesh instead of like as a grid. But like the grid, you can kind of see better how things are moving. So yeah, and this thing has like sort of water kind of motion going, like kind of like it's like Jello. You know, it's like Jello shed. Which this kind of leads us into what the next video is going to be about, which is going to be like kind of a quick primer of getting into what's that? Soft body physics. Because soft body physics is basically this. Getting things kind of gelatinely or whatever, kind of just moving around and then kind of going back to its not ready state, its resting state. So hope you enjoyed it. If you guys enjoy it, please, if you can, spare me $1. Go to Patreon and spare me $1. I want to buy a new laptop for development. So it'd be kind of nice. Something maybe in a couple of months, maybe maybe in January, like around my birthday. You know, because I'll have like Christmas money and birthday money all come in, and I'll take some Patreon money. I'll just group it all together and buy myself a really nice laptop. So if you want to help and donate to help me get a new laptop next year, please feel free if you feel like I deserve a tip. So now I'm done shamelessly plugging my Patreon. Please like and subscribe. I haven't done that in the last couple of videos because whatever. I don't get ad money from YouTube, so it doesn't really matter. So yeah, please add and subscribe. Why not? Maybe I'll get that award in like 10 years. And yeah, see you in the next video, and I hope you enjoyed it. Bye-bye.